welcome back to the last class of this week. We have been talking about these chemical reactors, the design principles in general, and in particular how we can modify the equations for the design equations for different kinds of reactors in terms of conversion, and ultimately some real problems of if you are carrying out a particular reaction in a particular reactor, what is the kind of parameters that are necessary to be controlled so that you can get a particular amount of conversion. So, we are developing all these things step by step. We started by talking about the rate law, because for any chemical reaction that you do, you need to know the rate law. So, that rate law basically tells you how the rate varies as a function of concentration. The second thing is that you have to find how the concentrations of these different species that are present in the system, they vary as a function of conversion. These things you can find from the stoichiometric table, and the stoichiometric table you can construct individually for different kinds of reactors, and we already told that they have some similarity as far as the flow reactors and batch reactors are concerned. And when you combine these two things, that is the rate law where the rate varies as a function of concentration, and the stoichiometric table which tells you how the concentration varies as a function of conversion, when we put them together you get an expression of rate as a function of conversion. So, you basically have known, you basically have now got the rate how it varies as a function of conversion. So, that you can construct those kinds of tables that I have already shown you, and a couple of problems we have worked out for CSTR. We will try to go back to those tables when we are doing other different problems, mainly for the reason of simplicity and for the reason of comparison between different kinds of reactors. So, we will continue in the same vein today. So, let me first start by summarizing what we already know. So, the topic is the same, design of chemical reactors, that we are continuing. The theme is the same for this particular week, and so let me then write down this simplified thing for you, means whatever we have understood until now: reactor, mole balance, and then we have in terms of conversion. This is at the heart of all the discussions that have gone on this week. So, the batch reactor. So, for the batch reactor your mole balance was, it is good to recap once in a while, so that you do not get lost in the stream of inflow of all this information. So, in terms of conversion your T is basically 0 to x a Na 0 by minus R a into dxa dv dxa by v, excuse me. So, that is batch. So, if you are looking at CSTR, then your mole balance equation is f v equals to f j 0 minus f j, molar flow rate in, molar flow rate out, divided by rate of generation of the species j, and then this can be expressed in terms of conversion, which is more practical for you, f a 0 into x a divided by minus R a. We also constructed a Levens-PL plot of f a 0 by minus R a versus x a in order to find out the value of v at a particular x a. Now, PFR, plugged flow reactor, the mole balance equation was dfj dv equal to Rj, and in terms of conversion your v equals to 0 to x a minus f a 0 by minus, so minus is already there, R a into dxa. Now, this is inside the integral because rate is also a function of conversion. And finally, for PBR, packed bed reactor, you have dfj dw, so as a function of the weight of the catalyst. So, that is equal to Rj or Rj prime, if you so please, Rj prime. So, then that will be W equal to 0 to x a, same form as PFR, instead of V of W, minus f a 0 divided by R a prime into dxa. Now, if you are looking at, so let us say we have already talked about CSTR in detail, how to find out the volume for a particular conversion. If we want to do the same problem for PFR, the volume for a particular conversion. So, let us say V PFR for a particular conversion of x A, what is the volume of PFR or plugged flow reactor for a conversion of x A. So, that is equal to 0 to x A f A 0 by minus R A into d x A. So, again if you plot the same graph f A 0 by minus R A as a function of x A, so your plot is like this. So, let us say, or as a function of x A. So, let us say you are looking at a conversion of x 1, your question is at a conversion of x 1, if you have to have a conversion of x 1, then what is the volume of the plugged flow reactor that you are going to use, then it is immediately becoming apparent to you that it is basically the area under the curve that is important. This area under this graph gives you the volume of the plugged flow reactor necessary in order to have a conversion of x 1. Why? This integral of 0 to say x 1, integral of this y dx. So, this is, let us say this is y, we are plotting against x. So, this curve, the area under the curve is basically integral 0 to whatever value here y dx. So, this is the area under the curve, nothing but the area under the curve. So, the area under the curve gives you the volume of PFR necessary to get a conversion of x 1. But if you are looking at the same curve and if you are saying what is the volume of CSTR, if you are using instead of a plugged flow reactor, if you are using a continuously start tank reactor, then what is the volume of CSTR that is necessary in order to get a conversion of x 1. So, that volume of CSTR that is necessary is nothing but this. So, from the graph itself you can see that the volume of CSTR necessary in order to attain a particular conversion is basically higher than the volume of PFR necessary. So, you see the beauty of the mathematics here. It is nothing to be feared, but rather you try to get the physical meaning out of that, what is useful for you. So, now the question comes, how do you determine this integral? That poses a problem. So, typically what we do is that we numerically evaluate these integrals. I will take you step by step through some of the most basic processes of numerical analysis to get the value of integrals. It is necessary ultimately, because even when you are looking for say polymerizations and all, you have to use the same kind of techniques, same kinds of different equations, that is at the heart of the chemical reaction reactor design. We are talking about ideal, of course, ideal CSTR, steady state situation, and also we are talking about the temperature being constant, say for example CSTR, if it is isothermal situation, temperature constant, then all these things are valid. If you are talking about temperature changing, then things will change. We will not go into those kinds of complexities, at least not for this course. So, the problem then becomes essentially to evaluate this integral. So, evaluation of the integral is nothing but finding the area under the graph. So, one of the ways in which you can do that is trapezoidal rule, a numerical process. Basically, this is a 2-point process. So, let us say, so this is a 2-point process. You want to evaluate an integral x 0 to x 1. The functional form is f x dx. The same thing f x dx. So, this is f x dx, because this particular thing is a function of x, which is the conversion, that is why that is f x. So, function of x. So, the general thing here is that h by 2 into f x 0 plus f x 1. Okay. So, h is the distance between the 2 points, h is basically x 1 minus x 0. So, it is nothing but saying, if you have, you are plotting y versus x and you have a curve like this, how to find out the area under the curve? You approximate basically. So, what you do is you generate a trapezoid. So, you generate a trapezoid like this. So, you generate a trapezoid like this. Sorry, this is a trapezoid. So, your curve is going like this. So, this is a trapezoid. Now, you find the area under the trapezoid, and that is nothing but this. So, let us say this value here is b and the value here is a, then integral a to b f x dx. So, this is an approximation of course, because this area is not exactly the same as the area under the full curve, but again numerical analysis goes to an approximation of course for you. So, this is a little bit not very clear. So, here is the curve. So, you are basically adding up these 2 points here. So, this is your trapezoid. So, the integral f x dx is nothing but h by 2 into f a plus f b, h being the distance between the two. So, h being the distance between the two and f a. So, f a plus h b, these 2 values. So, correspondingly this is the area of the trapezoid. So, that is why it is a trapezoid rule. Now, we will not discuss this thing too much. Something more important that we will discuss is Simpson's, what you say as 1/3 rule. This is basically a 3-point rule. So, whatever interval you have, you basically divide that in equally spaced even number of intervals. Whatever spacing you have, you basically divide that into equally spaced intervals. So, if you have to find the integration of the curve between these 2 points, then you divide that into equally spaced interval if possible. Okay. So, like that, say if you have 0, 0.1, 0.2, 0.4, suppose you want to find out the integral where the conversion is 0.4. So, for PFR then you have to find out the integral, the area under the curve up to the point where 0.4. So, then this particular integral will become 0 to 0.4. Okay. So, it will be 0 to 0.4 f a 0 by minus r a into dx a. So, then you can divide this into 2 equally spaced interval 0 to 0.2. So, the spacing is 0.2, the difference is 0.2 and 0.2 to 0.4. So, the difference is again 0.2. Then you can use some of these rules. So, equally spaced even number of intervals. So, these are equally spaced, and what are the number of intervals? 2 intervals are there. So, then you can use for example Simpson's 1/3 rule. So, basically it becomes something like this x 0 to x 2. So, x 0, x 1, x 2, these are the 3 points. So, the total interval is 0 to x 2, you divide into 2 intervals. The total spacing is 0 to x 2, you divide into 2 intervals 0 to x 1 and x 1 to x 2, and these are equally spaced. And then the formula that you have is f x dx equal to h by 3 f x 0 plus 4 f x 1 plus f x 2, okay, where x 1 is equals to x 0 plus h and h is equals to x 2 minus x 0 by 2. Okay. And in general, the form of the Simpson's 1/3 rule will be x 0, let us say you are integrating from x 0 to x n, f x dx, that will be equal to h by 3 into y 0 plus y n. So, the first ordinate and the last ordinate plus 4 into sum of odd ordinates plus 2 into sum of even. Actually, you do not need to remember all these things, because these things are already documented. So, when that interval is there, when you find out, when you have what is the power of this, if you have to have this kind of problem, if you have this kind of problem, then you find out for yourself which rule to use, and all those expressions for the rules, these are already in the literature. So, you find out, you put it there and you can get the conversion value. That is why it is important, but you need to know that such things exist. That is why I am just writing down all these things. Then there is another form, Simpson's. So, this is basically you are using your Simpson's 1/3 rule for equally spaced intervals, even number of equally spaced intervals, but you may not always be able to have even number of equally spaced intervals. So, you can use what you call as Simpson's 3/8 rule also. Okay. Just look at it as some of the techniques that I am introducing. So, basically then it will be fine for you. So, look beyond again some of these expressions and try to understand why we are using them. These are just tools, but you need to understand the tools in order to use them effectively for your own purpose. That is important. So, Simpson's 3/8 rule, basically it is the intervals in multiples of 3. If you can manage to have intervals in multiples of 3, then you can use this in multiples of 3, then you can use this Simpson's 1/3 rule. So, the general form of this rule is x 0 to x n, again this is the whole range, f x dx equals to 3/8 into h into, again this is the first ordinate, this is the last ordinate, plus 2 into sum of multiples of 3 ordinates because you are multiples of 3, those ordinates you just take, plus 3 into sum of remaining ordinates, okay. And your h is x n minus x 0 by n, where n is the number of intervals. So, if you can manage to split this whole range in the problem, whatever range is there, suppose you are talking for about 0.4. So, you are trying to find out from this particular table what is the plug flow reactor volume with a conversion of 0.4 for 40%. So, then you can actually see that you can, all the data that you have from there, you can divide this whole range into 2 equally spaced intervals 0 to 0.2 and 0.2 to 0.4. Then you can only use Simpson's 1/3 rule. Like this you have to look at some of these situations. Okay. So, and sometimes you may have to use both of them together. For certain region you have to use one of them, and for the other part you have to use the other one. So, in combination of that you may have to use that. So, what we will do now is the following. So, let us say we go into the same, we are going for the same table, again we are trying to find out what is the volume of plug flow reactor for this particular system that is necessary in order to get 40% conversion x a, and this is f a 0 by minus r a, all these values are there. And we have already found out what is the V CSTR, volume of CSTR or continuous start tank reactor necessary for 40% conversion, that is 0.82 meter cube, that was the volume of CSTR necessary. And we know from this graph, so we actually have already found out that it is the area under the curve that gives you the PFR volume, but this is the area for this rectangle, whole rectangle, that gives you the CSTR volume. So, basically you will have a value lower than this when you calculate this thing. So, you can use Simpson's 1/3 rule for this thing here. So, let me do this for you. So, I will just write down this expression again, x a, and then if you have f a 0 by minus r a 0, 0.1, 0.2, 0.4, and then you have 0.6, 0.7, 0.8. So, this is f a 0 by minus r a is 0.89. As I told you, you can find this out because you know how r a changes as a function of conversion. We have already discussed this. 0.1 is 1.08, this is 1.33, 2.05, 3.56, 5.06 I suppose, and this is 8. So, the question was obtain the volume of PFR necessary for a conversion of 40%. So, then this is, so you can actually have 2 equally spaced interval as I told you. So, 2 equally spaced interval for this. So, you can apply Simpson's 1/3 rule. So, one interval is 0 to 0.2 and the other interval is 0.2 to 0.4. So, Simpson's 1/3 rule. So, if you look at the expression for Simpson's 1/3 rule, that was this, when you have two intervals, specifically that was this. There is a general form also, but here this is necessary. So this is x0 to x2 fx dx, this is the integral you want to find out, and that will be equal to h by 3. Let me write down the formula again, x0 fx0 plus 4 fx1 plus fx2. Okay. So, if you are putting these values here, so what is the value of h? H is nothing but x2 minus x0 divided by 2, because 2 is basically the number of intervals you have. So, that is here x2 is 0.4, x0 is 0 and 2 is there. So, this is 0.2. So, this is 0.2. Now, what is the value of x1? That is necessary, because fx1 is basically the value of fa0 by minus ra, where x equals to x1. So, what is the value of xa that corresponds to the value of fx1, that you have to find out. So, x1 is nothing but x0 plus h, x0 is 0 and h is 0.2. So, x1 is 0.2. So, fx1 is nothing but f 0.2. So, that means this value is the value of fa0 by minus ra at xa equals to 0.2. So, that is 1.33. Same way fx2 also you can find out, because fx2 is the value of fa0 by minus ra at x equals to 0.4. So, then if you put all these values here, this will be 0.2 by 3. So, fx0 is basically the value of fa0 by minus ra at xa equals to 0 plus 4 into fx1 is the value of fa0 by minus ra at xa equals to 0.2 plus fx2, it is the value of fa0 by minus ra at xa equals to 0.4. Okay. So, if you calculate this thing, it becomes 0.55 meter cube, and as we have already shown you before. So, for the same conversion of 40%, if you are using a continuous start tank reactor, you need a higher volume 0.82 meter cube. If you are using a PFR, which is a plugged flow reactor, you require lesser volume. So, graphically also we have shown, and when you do the calculations also these become apparent. So, then in general we can write V CSTR for a particular conversion x equals to x a will be higher than V PFR for a particular conversion x equals to x a. Okay. So, the final thing that we would like to do here, I mean we could go on and we can do lot of expressions here, but one thing you should remember is that we are using a technique, these tools. So, this particular workout that I have done is, later on if you find a problem where you have to design the reactor, which reactors to use, so on and so forth, what is the volume of the reactor, then you can go to some of these numerical approximations and you can use them. So, I am telling you how to use them. You do not need to remember the expressions of those, say Simpson's 3/8 rule, that is there, but you need to keep in mind how many intervals you can divide it into, and then what kinds of techniques you can use correspondingly, whether you will use Simpson's 1/3 rule or whether you will use Simpson's 3/8 rule. So, that is the thing here. Now, if you are, say for example, if you are looking at this particular thing, say okay, if I ask you, if you are using two PFRs, two plugged flow reactors in series, and you are trying to achieve 80% conversion, and the outlet from the first plugged flow reactor is giving you 40% conversion, then what is the volume of the two plugged flow reactors? It is a similar question to when you are having two CSTRs in series and the outlet of the CSTR1 has a 40% conversion. So, that is then the inlet input for the CSTR2, and the outlet for the CSTR2 is giving you 80% conversion. In this case, you can just rephrase this same question for PFR. So, if you are considering the same question for PFR, then the total volume of PFR, suppose 0. So, in the first PFR PFR1, your inlet, your conversion is 0. So, it is coming out as say the conversion is x1, suppose. This is the input for PFR2 and the output is x2. So, suppose I want to get a final conversion of x2, the intermediate conversion is x1 after it leaves the first PFR, then what is the total volume? The total volume will be the volume of the first one, which is 0 to 1, 0 to, I will just write down it in a new page. So, what will be the total volume? So, the volume of the first PFR will be 0 to x1 into Fs0, 0 to x1 integral Fs0 by minus Ra into dxa plus x1 to x2, this is the second volume of the second PFR, Fs0 by minus Ra into dxa. So, the problem essentially reduces to finding out the two integrals where x1 is equals to 0.4 and x2 is equals to 0.8, and you can immediately see that when x1 equals to 0.4, already we have done this particular calculation. You can have a Simpson's 1/3 rule, because you can divide into two equally spaced intervals 0 to 0.2 and 0.2 to 0.4. Similarly, from 0.4 to 0.8 for the second integral, for the derivation of second integral where x1 is 0.4 and x2 is 0.8, what you can do is that here also incidentally you can divide it into two equally spaced interval 0.4 to 0.6 and 0.6 to 0.8, the spacing being 0.2 between the two and 0.2 between these two, and you can apply the Simpson's 1/3 rule again. You can actually work it out yourself, and also what you can do is that you can then try to play around with this, and let us use, you can use only one PFR, only one plugged flow reactor in order to get the 80% conversion. We did this correlation with CSTR. For the same total conversion, if you split it up between two CSTRs, then the total volume of CSTRs necessary is basically lower than the individual CSTR that was used for the overall conversion. In this case, here you can do the same treatment for plugged flow reactor, and I will not show you, this will be a homework for you. You can actually show this, that suppose you want to get 80% conversion at the end, and you are using one PFR, so that your inlet, your conversion is 0, outlet, your conversion is 80%. If you integrate, you get the volume. If you use two PFRs, the first one, the outlet is 0.4, that is 40% yield already achieved. The second one, this 40% yield, after this yield, this composition is the inlet input for the second one, and the outlet output is 0.8. So, if you now split it up into two reactors to achieve the final goal of 80% conversion, it can be shown how many, no matter how many PFRs you split it up into, the overall volume that you have to use is the same. Whether you are using several PFRs to achieve the same yield, or whether you are using one PFR to achieve the same yield, the total volume is the same, because ultimately what you are trying to get, if you look at the graph, it becomes clearer for you. If you look at the graph, so it is the area under the curve. So, no matter how many divisions you make, so maybe the first PFR will give you a conversion here up to this, second PFR, this is the inlet conversion, I mean this is the inlet composition, and this is the outlet conversion. Third PFR, this is the inlet composition, this is the outlet conversion. So, everything will fall under this curve. So, overall volume will be the same, but this is not the case when you are talking about say your CSTR, because when you are talking about your CSTR, if you are plotting Fa0 by minus Ra versus Xa, you have this kind of graph. Okay. So, this is the area under the curve when you are using only one CSTR to achieve this conversion. If you are using more than one CSTR, suppose you are using two CSTRs, you start with this conversion suppose. So, for the first CSTR, the area under the curve will be this. For the second one, you start with this input and you get this output. So, the area under the curve will be this. So, this total area is basically excluding this particular area, that means the total volume, this area is equal to volume in this case, the total volume necessary will be lower than the volume of the individual CSTR if you are using only one CSTR. So, graphically also you can show this thing. So, what we will do is we will stop here today, and in the next class we will talk about the chemical reactors a little bit more. A couple of problems we will do, maybe one of the problems will be related to polymers, and that is all that we will do as far as the principles of chemical reactors are concerned. So, and afterwards we will start talking about industrial preparation of polymers as the topic once we finish the talk of chemical reactors. So, till then, thank you and goodbye.